Good afternoon to everybody who's here in person, and good afternoon to those who are joining us online. My name is Adrian Edkins, and I'm from Rhodes University, and I have the pleasure to chair this afternoon session. So we have two speakers today. The first speaker is Dr. Malcolm Hillebrand from the Mathematics Department at UCT. He works in the nonlinear dynamics and chaos group and is going to speak to us today about chaos through computing, condensates, plasma, biology, and beyond. Welcome, Malcolm.
Great. Thank you very much, Adrian. And yes, hello, and thank you very much to Vanna and all the CHPC team, both for the invitation to come and share our work and for all the hard work that you do to allow us to do our work. We really do appreciate it. So yes, I am neither a material scientist, nor a chemist, nor a biologist. Therefore, I am in the minority. I don't know if you saw Anton's slides yesterday with the posters. There was one physics poster. I will say, he did get an award, but yes, so I'm even further afield. I'm from applied mathematics, and I will be giving you a talk about how chaos is used, how we study the uncertainty of life in a variety of systems. So I will introduce our group that I am representing here this morning, afternoon, it's morning somewhere. And I will talk about what exactly we do and how we do it. There'll be a smashing of technical details and some computational stuff and some numerical physical stuff. And then I will give you a flying tour through our research to try and give you a flavor of the sorts of problems we tackle. Grand. So let us begin. Yes, now it breaks. Good. So this is our group with some pictures. So the big cheese, or as we like to call him, the principal investigator, Professor Harris Skokos, a couple of postdocs, some PhD students, master students, and then two graduated PhD students who are still associated with the group and do their research elsewhere in France and Uganda. So we all do a variety of projects, and there's quite a spectrum of stuff that gets done by this group. The spectrum is kind of as follows. We have a general umbrella of Hamiltonian dynamics, okay? That word doesn't have to mean anything to you. Basically, you give us a set of equations of motion, and we can do science with those equations of motion. Those equations of motion can come from DNA, graphene, disordered lattices. Just a quick definition. Disordered just means that different beads have different properties, right? So it could have different masses, difference of springiness, whatever, disorder. Chemical reactions, granular materials, actual physical balls bouncing off each other, plasma fusion, and galactic dynamics. So we do the whole spectrum, right? No job too big or too small. There is chaos everywhere, and we have the tools to study those systems. So the things that we compute, right? What do we actually do once you have these equations of motion? We do, typical physical quantities. So like you would be interested in whatever, like with the DFT, you compute free energies, you compute different structures. We do the same kind of thing. So in a lattice where you might want to see how a wave is spreading, we'll look at that. We'll look at the literal wave propagation, the energy profile along the lattice, and the period of a star orbiting a galaxy, those physical quantities which are understandable in the real world. We do, of course, have to compute chaos quantities. So if you're not familiar with chaos theory, essentially it's the idea that if you make a very, very small change to your initial condition, you get a very large difference at the end, right? The famous butterfly effect. Butterfly in Tokyo flaps its wings and causes a hurricane in Nevada. Choose cities of your choice that are far apart, right? Very small change, very big difference. That's chaos. I meant to bring a little rubber egg with me, but you can think of a rugby ball, right? If you've ever watched rugby, it's so very hard to predict how a rugby ball is going to bounce, right? So they want to try and catch it before it bounces, because once it bounces, no matter how much rugby you played, it could bounce any direction. That's essentially chaotic behavior. You know it's determined. Once the rugby ball is in the air, it's going to do what it's going to do, but you don't know what that's actually going to be. And so we can measure this, right? Depending on how far these two nearby initial conditions diverge, right? How fast they become different, that tells us how chaotic it is, right? If they stay together for all time, that's not very chaotic. If they go far apart exponentially quickly, that's pretty chaotic. And how fast they diverge quantifies how chaotic it is, right? And this is the kind of thing we will study. We'll take these deviations, and maybe we have, we're computing one vector of positions, and we'll take another vector, and we'll calculate the deviation between those two vectors, and that deviation vector tells us about the growth. Good. So in terms of our numerical tools, one of the highlights of our group is that because we mostly work with Hamiltonian systems, again, you don't have to know what that is, it's just a certain class of physical systems, we can use symplectic integrators, which gives us this nice behavior where our error is bounded for all time. And if you've ever worked with long-time numerical simulations, your error grows, right? Normal Runge-Kutta, fourth order, your error is growing, but we have tools to circumvent that. And so we can actually go to very long times while maintaining accuracy. And this is key to almost all our research. The other thing we do is we work a lot with multidimensional lattices. The system is lots and lots and lots of particles, which all the chemists and the biologists are very familiar with, right? Essentially, once you start looking at any sort of meaningful system, you can have hundreds, thousands, millions of atoms, and those are the cases that we deal with, and that requires a lot of careful parallelization and good use of CPUs. So, technical considerations, we write our own code. We do not really use a lot of packages because they don't support the kind of things we do. So we write our own code, we optimize our own code. These are the languages we mostly work in. C++ and Qt are slightly less, but I'll discuss that at the end. So stick around for the high performance computing highlight. Yeah, sort of different people compile differently, but again, always it's a conscious choice. So we don't just pick a compiler, we will test, benchmark. Generally, I found that iFort for Fortran tends to be the best. And I've tried, occasionally, NV Fortran does a very close job, or occasionally it's slightly better. But in general, I found iFort to be the best, just the way it is. C++, ICC is also pretty good, but I found less importance there. It's a side note. Produce lots and lots of data, right? So we perform simulations with these symplectic integrators, get a lot of data, and stored in whatever is most optimal that we can then analyze. And this is on the terabyte scale, so not huge data, but just large enough to be inconvenient. And then, of course, we analyze this data and extract all the relevant information that we want to get, those quantities that we want to compute. So taking all of these into account, the computational details, the technical details, data. Okay, why do we need the CHPC? What are we getting from this? The answer is very simple. 15 million CPU hours, which for our little corner of the universe is quite a lot. And it was kind of mind-blowing to put this into CPU years and think, dang, we'd run these things in serial on our little desktop. I would have been, the Earth would probably be shattered before I get my PhD. So I'm deeply grateful for the CHPC resources, which allow us to do this monstrous parallelization very efficiently. So yeah, that's just a number. Good, so let's do our flying tour. Welcome aboard. And the first stop is at nonlinear disordered lattices. And so this in some part was where the group actually started. Professor Skorkos is certainly one of the world experts in this topic of studying disordered lattices. And essentially, these lattices can model all kinds of systems. So Bose-Einstein condensates, more complicated crystal structures. So in 1 and 2 dimensions, right? So 2-dimensional lattices become very, very interesting and of course, expensive. Again, stick around to the end. But with the study of lattices, we can understand how these structures work and especially how energy spreads and the chaos that is inherent to this. And so some of the HPC highlights, the dynamic lattice size. So consider that you have a wave spreading in a lattice and spreading out, and I'll show you in a second. You don't want to be integrating, these sites at the end, which have no energy, no motion whatsoever. You're just wasting your life in CPU time, and you get these nasty emails from CHPC saying that your jobs are wasting time. So what you can do is you can just extend your lattice dynamically as you go, which then means that you're only actually integrating what you care about. OpenMP for parallelization, again, symplectic integration, and then some clever data analysis stuff at the end to make results understandable. So why this is important is that actually there's a Nobel Prize given for this. So we're not just playing around with random stuff that no one cares about. It's actually important and really fundamental to a lot of laser physics, waveguide physics, any kind of motion through medium, which is most of life. And so we investigate this in nonlinear lattices, particularly the role of chaos in these things. And so we get these kind of results, right? Where you have an energy profile, where as we go up in time, you have the spreading of the initial wave packet, and a DVD which quantifies where it's most chaotic, okay? Don't have to worry about the details, you can ask me afterwards. But essentially, we find that we kind of get these two regimes in the majority of nonlinear lattices. We have a weak chaos, where you can see it spreads kind of more slowly, observe the x-axis. Whereas in the strong chaos case, we spread much more quickly, and the chaos is stronger, and the chaos is central to the spreading of the energy, right? This is the essential finding. Moving swiftly onwards, flying tour, I told you. Dynamics of granular chains. So what happens when we have this kind of granular matter? We have these actual physical balls bouncing off each other, and you can model this. I think actually many of you will probably have a bit of experience with these kinds of granular systems, because you can model a lot of fluids, a lot of interactions using these granular approaches. So it's actually extremely important for a lot of really hot topic research right now. And again, the same kind of thing that we need to do, parallel computations, because we need lots and lots and lots of statistics. We can't just take one random case and be like, oh, nice, because we need to be statistically sound. And the whole point of this really intense HPC approach is that we can be certain that our results are not statistical anomalies. And that's kind of a theme going through all these results, is that we make sure that we are statistically reasonable. Good, and so we kind of get similar sorts of results, where if we take some kind of model like this, where we take, right, an actual physical granular chain with some bits of plastic connected, model all the pieces together, and we get spreading results, right? So like we had for the earlier case, if you take a nice linear, undisordered, ordered, opposite of disorder, order, English, this lattice, we get a straightforward spreading, right? It just keeps spreading. There's no localization because there's no disorder. This is true in granular chains as well as in the original lattices. Of course, we throw in disorder. So we take balls of different sizes, different masses, and voila, Anderson localization. We have this beam down the center, which is corresponding to this localized energy and localized chaos. Good. Granular chains, bravo. Plasma, right? So we've been hearing a lot about plasma fusion, all this stuff going on. And you may have seen this kind of tokamak structure before, where you have these accelerating particles, which are used to create plasma. And you better believe that those particles are behaving chaotically, right? They're having these complex magnetic fields, which are trying to keep them right where they're supposed to be. It's the same in actually particle accelerators, where you desperately want your beam to be as precise as possible. It's scattering, it's chowing the sides of your beam, the sides of your tokamak, and becoming dangerous. So once again, we would like to understand what's going on with these so that we can help optimize and help inform decisions about how to design these tokamaks. And so a representative result, you're welcome to just observe the pretty pictures and see the colors. But essentially, the point that we make is we can discover patterns. This is our angular coordinate theta as we whirl around at relativistic speeds. And you can see patterns in how the particles and the magnetic fields form. And we can color this by how chaotic it is. And so we can find chaotic regions and stable regions. And this allows us to say, okay, this is probably where we want to focus, because we want to keep out of the chaotic region and try and stay in the regular region where we understand what's happening. And if we make a tiny mistake in our initial condition, it doesn't spiral out of control, right? That's why we like regular behavior. Bam. Chemical reactions. So many of y'all are working on chemical reactions and trying to understand what on earth is going on at those transition states. And as mathematicians, we look at this and say, yes, we want to help. So we simplify the heck out of everything, get some nice simple models which we can understand, and we can do things mathematically, and we can do things computationally. So we do much simpler computations, but they kind of support theoretical predictions that we can make, and so we can understand, for example, this kind of potential well where you have two kinds of reactants, which maybe from one angle they shoot across, and you find that one kind of reactant always leads to the same kind of product. We call this dynamical matching. And then from the other side, you have another reactant. It could have a 50-50 branching ratio or something like that, right? And so these kinds of things, we confer a different kind of HPC at, right? So we have the DFT, the force field computations to understand direct dynamics of these reactions, but we can also take these potential energy surfaces and study them. Another brief highlight, at the opposite end of the size spectrum is the motion of galaxies. or particularly stars around galaxies. And so here we have a nice pretty picture of a very, very, very small torus, where if we have a stable orbit and you perturb it slightly because it's regular, it means that everything stays nearby, right? But if we have an unstable orbit, we start getting these beautiful figure 8 patterns, which is telling us that actually this orbit is unstable and is starting to disperse. And if you run this longer, you'll find your star shooting off to some infinity, which is not good. And these structures turn out to be very important to the morphology, the sort of spatial characteristics of galaxies. Not an astronomer, but it's really cool. All right, so now we get to the meat. This is the part that I worked on most. I've been involved in some of the other projects, but this part now is primarily mine, and also the biologists out there might appreciate this a bit more. So we can also apply these models to DNA. So in particular, we take this nice DNA molecule, we look at the base pairs and say, those look like springs, and we can model that. As mathematicians, we just create some analytic potentials, we fit them, and we can model DNA base pair fluctuations. And as I will describe now, it turns out that we want to study very rare events. And so these rare events require large statistics. And when I say rare events, I mean rare events. And so we need long time integrations. So one of the things that we're studying at the moment is the relaxation of the DNA molecule after some perturbation. And that complete relaxation back to equilibrium takes a heck of a long time on the molecular scale. And so with our coarse-grained model, we really need to go accurately to long times. That's possible by symplectic integration. Equation fine-tuning, I'll discuss this more later about graphene, but it becomes very important whenever you're doing these mass simulations, a little increase in the number of operations you need to do per step really becomes costly. So we want to minimize that as much as possible. And then essentially parallel data analysis. We produce terabytes of data. You don't want to make Werner send you an angry email, so you try and clean up your luster as fast as possible. And that means condensing your data into a more manageable format. And that requires parallel computing, otherwise it takes weeks. So here we have parallel to produce the data, parallel to analyze the data, and we're still seeing why CHPC is so central to our workflow. So one of the focuses in particular is on bubbles. Bubbles is a thermal opening in our DNA molecule where it just breathes. You get artificially created bubbles, of course, which we use in transcription, where the RNA polymerase comes along, opens up, and allows the RNA to encode. It's been a while. I'm not a biologist. But particularly, we want to study these kinds of openings, where we have these spontaneous fluctuations. Because it's a thermal process, there are going to be these natural openings, and some parts of the strand will be more likely to open than others. So that is one of our first questions. How likely, at a given region of our DNA sequence, are we to see these fluctuations? Do they happen often? Do they happen rarely? What affects that? And how long do they last? So this is the much more interesting and much more difficult question, because how likely are they? You can do that Monte Carlo simulations. You can sort of look at some structural stuff and say, all right, this is probably what's going to happen. But to study the lifetimes, you specifically need dynamics, right? It's a purely dynamical process and becomes very important to have detailed data. So that's quite spicy. And then the question, of course, well, can we as mathematicians actually be vaguely useful to our friends in biology and say, well, does this actually affect transcription? That's a big question. And then because we're chaos theory people, we have to ask the question, where does chaos fit in? And when I say rare, this is a graph of the probability of picking an arbitrary base pair and it being part of a bubble of length L. So if I want to pick a bubble of length 10, so let's say I choose a base pair, and so depending on the constituent base pairs of the sequence, you get slightly different probabilities. Of course, 80 base pairs, for those who don't know, are weaker, fewer hydrogen bonds, GC more strongly bonded. So it doesn't make too much of a difference. If I want a bubble of length 10, I go here, I'll have less than 1 in 1,000 chance of picking a base pair in such a bubble. Transcription bubbles, for example, are between like 11, 13 base pairs long. So that's sort of our critical region. And if we want decent statistics, very rare events, exponentially rare events. And it turns out that the lifetimes are exponentially short as well. So if we want to study lifetimes, double exponentially rare, which means doubly exponential amount of data required. Good. So that's our solution. Data. Lots and lots of data. Everyone's favorite. So now again, we have this twofold challenge of the simulations as well as the data. So we have to deal with both. Great. And combining efficient code wrangling, as I technically call it, as well as the parallel power of CHPC and HPC computing in general, HPC computing, anyway, it allows us to break new ground. Actually, a lot of what we've done is like it blows previous work out the water in terms of statistics, in terms of sheer amount of sort of rigor and data supplied. So we actually can be sure that we don't just happen to find a rare event and say, we have a rare event where we want to see it, therefore we are correct. But rather we can go through and check, okay, do we actually reliably see these rare events and not just get a statistical fluke, which we want to believe. Good. So an end result that we've got, and I'll show you some nice colorful pictures, is we can compute these bubble lifetimes for particular promoters, right? So we take, in this case, an adeno-associated virus P5 promoter. We look at the wild type, and we look at a transcription inhibiting mutation. So the wild type and the mutation, and we compute the average bubble lifetime for bubbles starting at a certain site. So each pixel of this image is something like, I don't know, several million data points. And each of these graphs is about a terabyte of data, maybe a little bit more, which is neat. And it means that we can look at each of these pixels. So I can look at the site and say transcription start site 1. I can go, what are the probability of seeing a bubble of exactly length 5? And I see, okay, the probability, the lifetime. Typical lifetime is about 0.2 picoseconds, according to our relative timescale, right? T's and C's apply, timescales may vary. And we can do the same thing for mutation and play spot the difference. So if we put this flip 2 base pairs at the transcription start site, we know kills transcription, what happens to the dynamics? And definitely there is some change here in terms of the lifetimes, but that's kind of hard to see. And so, like sensible mathematicians, we just compute the relative difference of the lifetimes and say, okay, these regions where it's white, there's no relative difference between the wild type and the mutation. But here, this blue channel is where we have a 20% decrease in average bubble lifetime. So in some sense, this makes a lot of sort of logical sense in that we mutate AT base pairs to GC. It decreases the lifetimes because they're more strongly bonded, and it results in this decreased lifetime. So there's this possible link between lifetimes, and there has definitely been a previous link found between bubble probabilities and transcriptional activity. Good. So in my last few minutes, I will be talking a little bit about graphene because it's the most interesting HPC application. So graphene is an extraordinary material, and we have a atomistic model of graphene, which was produced by some collaborators of ours in Greece. And we want to study this to see, okay, can we take make some links between chaos and the glory that is graphene? And for context, this is just some fun math because I have to include an equation to justify my affiliation. Essentially, this is the energy function for our graphene model. To find the equations of motion, we have to take derivatives of this. And I could not possibly put that on a slide. To study the chaos, we need to take second derivatives of this. And I refer you to the MSc thesis of Arnold and Gapasare, where he has entire pages of these equations, and it's worth a read just for the shock value. Good. So you don't need to care about these equations. You just need to be convinced that when we come to HPC applications here, we throw everything we have at this thing, right? We want to study a meaningfully large lattice of extremely complicated equations. We need, whatever we can find. So I spent some time in Germany with some very smart people, and we wrote code which, using HPC specialists, physics people, we combine them, throw everything, OpenMP in parallel instances to get good data, repeatedly rewriting our code, repeatedly rewriting our equations and re-optimizing and like counting operations and trying to minimize those and checking that everything's efficient. Rearranging our numerical schemes. So we take our integration and we just like anywhere we can possibly get a 2% increase, it's extremely valuable. And ultimately, CUDA, which is very flashy. And if you want to do large simulations of many particles, GPUs are amazing. Oops. Good. So some actual computing graphs. The effect of parallelization on our graphene lattice is essentially that for typical lattice sizes, sort of medium to small for our purposes, we get definitely decent speed up, right? So as we throw on extra CPUs, at first we get pretty good speed up, especially for the larger lattices. Okay, we expect this larger lattices should be more amenable to parallelization, but essentially, like up to 4, we get really good value and starts decreasing. And since we need many instances to run, it turns out that this best balance is with 4 CPUs and then just fill up all available CPUs. And that's kind of our sweet spot, where it doesn't take forever to run, but we get enough data. We also created the GPU version of this code. So the code was written in C++, and so we made a Q-to-C version of this code. And unsurprisingly, for very large lattices, the GPU is absolutely amazing. So on the left, we see a graph of the wall time. So this is just the actual time it takes from start to finish, depending on the number of particles. So as we shoot up, essentially, the compute time scales linearly. 4 CPUs takes forever, 24 CPUs takes slightly less forever, and the GPU, okay, well, looks flat. This graph isn't very elucidating. If we rescale, according to the CHPC estimation of 1 GPU hour is 40 CPU hours, and we account for the actual CPU time, turns out for very large lattices, the GPU still hilariously outperforms the CPU. This is kind of what we're finding in the modern age of accelerated computing, but this is kind of neat. So when we really want to probe the limits of large lattices, this is what we can do. But the CPU code works really well for small cases, and parallel CPU code does a good job. So we get some results just to sort of demonstrate that we actually use this. We didn't just play around. With different kinds of graphene nanoribbons, we can study how the chaoticity changes. This gives us some estimation of the stability, the dynamical stability, which is quite neat. And that brings us to the end. So essentially, the takeaway is that high-intensity, high-performance computing allows us to study an enormous range of physical systems and understand the chaos inherent in them. We need a lot of optimization and parallelization to work with these many degrees of freedom models. Our understanding of physics, chemistry, biology, all these things can definitely be enhanced by studying the chaoticity. So chaos is part of everything, understanding that is useful. And the CHPC genuinely enables us to go where no one has gone before. So, okay, some publications for the record that use the CHPC and theses, and thank you for your attention. Trying to go back to the, there we go.
Is it on? Can you hear me? Okay, thank you. Thank you very much, Malcolm. Do we have any questions? Yes, Quinn, we'll start with you.
Thanks very much, Malcolm. Wow, this is awesome. I actually have a couple of questions. So the first one's maybe just a more technical one on the coding. You mentioned quite a few different languages. Have you guys looked at Julia at all?
I'm glad you asked.
It's great for dynamical systems.
Yeah, I attended the Dynamics Days conference in Scotland a few months ago, and there was a very strong evangelist for Julia there. It's definitely on my radar. So I would strongly recommend it to anyone who is thinking about dynamical systems, and I would recommend it to myself. Yeah.
No, I mean, they've done a lot of work on developing the integrators and everything for specific
exactly.
forms. And then, maybe following on from that on the integrators, these symplectic class of integrators. I mean, they're presumably time explicit methods, are they? Yeah. So, do you have much of a sense for kind of how the stability trades off against the compute power you need to actually calculate a time step? I mean, like RK4 and things like that give you reasonable stability, but obviously the cost of more steps and things.
Yeah, so look, I think one stability consideration is certainly the largest time step where it supports where your integrator is stable. So depending on how accurate you need to be, you might find that a particular integrator can give you accuracy of 10 to the minus 12, but you don't really care about that, and it becomes unstable at that point, then no, it's not valid. But then when there's such a range of these symplectic integrators, you can find one for every application. You can find, you do get implicit ones, certainly. But basically, yeah, you can pick and choose.
Thanks a lot.
So the stuff you did on the lattice, what do they call them? The lattices early on.
Which one? The disordered lattices.
Disordered lattices. Yeah. That's right. And you said you can extend it to 2D. Can you go to 3D?
Yes. So the 2D lattice accounts for like the largest part of our 15 million CPU hours. And so I'm working with Mani, who's in France at the moment, and we're trying to think of how we can go to 3D. It has to be in a GPU, definitely. But yeah.
So do you think it would actually? Do you mind if I just that was part of the same? So if you were say to instead of applying it to a molecule, if you were to apply it to something like a big girder structure like a bridge or something, do you think you'd be able to actually get nonlinear shockwave or like plot a shockwave moving through such a structure?
Yeah. So anything you can model, you can definitely see these things, right? So we can see like these kind of structures in DNA, for example, that you see in physical reality, you can reproduce them in the models, and these kind of mechanical engineering structural things. You definitely could
to do in traditional FEA, if I remember.
Yeah.
From what I know of it.
Yeah. Okay. Cool.
Okay, thank you. I think in the interest of time, we'll just thank Malcolm very much for a very interesting presentation.